So at the very beginning of the year, we were talking about just elements. Then we moved on to talking about bonding between elements. Now what we're going to talk about is the forces not within that element or a bond, but the forces between neighboring elements or bonds. And this is really, 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 really important because you never have just one atom or one molecule. So the forces that hold them together, important. But I would argue the most important thing really that we deal with every day when we look at phase changes or boiling points or evaporation or even wash our hands are the forces that are holding neighboring particles together. And those are called intermolecular forces or IMF forces. Okay? And I'm just going to go through and do some examples that we've seen already. Okay? And the first thing that we want to do is draw the Lewis structure. So let's say we had H2S. Okay? So the first thing we're going to do is draw the correct Lewis structure for H2S according to the correct shape. And the shape is going to become pretty important here. Okay? So we want to identify, is this molecule polar or is it non-polar? So who's pulling harder on these electrons? Well, a general rule we talked in class today is just whoever's more to the right on the periodic table. So S is a little bit down, but it's more to the right. Okay? And then I ask myself, is there a net dipole? And what I mean by that is if these two arrows, these two dipoles, the direction of the pull of the electron, were to smash into each other or pull away from each other, would there be net movement? And you notice here, if this one and this one hit one another, we would have net movement in the forward direction. So what that means is this molecule is a polar molecule, meaning there is a net dipole. And if it's a polar molecule, it will be left with charges. So let's go ahead and redraw this. Since it's a covalent compound, we will have a partially negative charge here, and we will have a partially positive charge here. And that's because the electrons in this bond are closer to that S. Okay? So what will that intermolecular force or interaction diagram look like? We call it an IMF diagram. Okay? Well, that IMF diagram is going to bring together the partially positives and the partially negatives here. So down here, you're going to have the S. And up here, you're going to have the H. We're going to have our lone pairs. And this is going to be a partially positive. This is going to be a partially positive. And this is going to be partially negative. And we have this force right here. We call that an intermolecular force. Okay? That's the intermolecular force. That's the force that's holding them together. Now, this is a pretty strong force because you have a charge being attracted. So this thing would tend to be in higher states, like liquids or solids. And we have a name for it. So this is called a dipole, right here, and this is called a dipole. So this intermolecular force is called a dipole to dipole force. Let's do another dipole to dipole force. Okay. So let's look at something like CH3Cl. So when we draw the Lewis structure for CH3Cl, doesn't matter where you draw them, but you're going to end up with something like this. Okay. So the first thing we need to do is draw our dipoles in. And we learned in class today that a CH bond is always nonpolar. Don't even worry about it. So we have a dipole here. Cl's more to the right. Okay. So obviously, if we have just one arrow, we are going to have movement to the right. And this thing is then going to be called polar. Okay. So if I were now to draw the Lewis structure again with the dipoles, I'm not going to draw anything on the CH's, but I'm going to have partial charges on this, and partial charges on this. So when you have more of them, and you always do have more of them, the C is going to be here, and the Cl is going to be over here. Okay, and we got our partial charges there, partial positive, partial negative, and again, because this is a dipole, anytime you have a partial charge that's created by a dipole, remember that right there is called a dipole. This force, this intermolecular force, is called a dipole to a dipole. It's a type of IMF, or intermolecular force. So we have a charge and another charge. Therefore, you're going to tend to be in the liquid state or even the solid state. Okay. Let's go ahead and do one that's nonpolar. So if we had something like N2, we do the Lewis structure for that, and we see that there's no movement here. There can't be any movement, okay, at all, because there's no dipole. So this is a nonpolar molecule. Okay, so the intermolecular force diagram for this is going to be really interesting. It's really simple. You just draw them far apart from one another. Okay, and there is a force that's in between these things, but we don't really pay much attention to it. It's a really weak force, and we call that force a London dispersion force. Okay, so it's a partial attraction that happens just given the fact that there are electrons there, and those electrons tend to move, and once in a while you can get an attraction. But in general, it makes sense. We know that nitrogen tends to be a gas, and why would it be a gas? It's a gas because it's separated. Okay, they don't want to be with one another. It's not about these bonds. These are the intramolecular bonds. These are the bonds between them. Let's look at a different one. Let's look at something like CS2. Okay. Well, if we draw the Lewis structure for CS2, there are dipoles here. But because of its shape, they're going to cancel. Notice, if these two things were playing tug of war on one another, one is pulling in this direction and one is pulling in this direction, they will cancel out, and you'll be left with no movement. So it's a molecule that is non-polar, but it does contain dipoles, or polar bonds. Okay, another word for dipoles is simply polar bonds. So it's a non-polar molecule with polar bonds because they cancel. Okay, so this would be the same thing if these were heading in. Okay, as long as there's equal force in equal or opposite direction. So what's this going to look like? Well, it's going to be very similar. You do not draw the partial charges. Okay, even though there's technically a partial negative here and a partial positive here, we don't draw them because they're canceled. So we just draw these really far away from each other. Okay, and sometimes I like to draw, we don't even need to put anything in there. And that region in between is called a London dispersion intermolecular force. So it's an intermolecular force that we really don't see, and because we don't, much like nitrogen, it tends to be